This podcast is part of the Democracy Group.
Welcome to Outrage Overload, a science podcast about outrage and lowering the temperature.
The situation here in Santa Monica, California is very fluid. You can see police here now firing tear gas into the crowd.
More than 106 days of rioting in a Negro section of Los Angeles left behind scenes reminiscent of war-torn cities.
Jim, just a few moments ago, something believed to be a plane crashed into the South Tower of the World Trade Center.
It's 1950, Los Alamos, New Mexico. Some of the most brilliant minds on the planet are walking to lunch. They're joking about a New Yorker cartoon. They're complaining about the cafeteria food. In the middle of this mundane midday chatter, Enrico Fermi, the man who built the first nuclear reactor, just stops. He looks up from his sandwich and asks a question that still haunts every telescope we point at the sky. Where is everybody? Think about that. In a galaxy with hundreds of billions of stars, we should be seeing a cosmic neighborhood bustling with life. But instead, we see a void. And if we really are the only ones standing in that silence, maybe it's time we started acting like it. And that's what we're going to talk about on this episode of the Outrage Overload podcast. I'm your host, David Beckmeyer, and today we're joined by a man who spends his days looking for life in the cosmos.
I'm Caleb Scharf, and I'm the senior scientist for astrobiology at NASA's Ames Research Center in California. And before that, I was the director of astrobiology at Columbia University for many years, and I'm also a popular science author.
Dr. Caleb Scharf is here to help us zoom out from the outrage machine and look at the overview effect of our fragile, lonely island in the stars. Caleb Scharf, thank you so much for making time for our little program.
Oh, my pleasure. Thank you.
So you're the senior scientist for astrobiology, and I know we could sort of look it up on Google it, but can you just tell us a little bit of what is astrobiology?
It's a good question. So astrobiology is really about the search for life in the universe. And that means also a search for how life comes to be, the origins of life. It's a quest to understand the nature of life on Earth, and then a quest to expand that to the possibility of life elsewhere, whether it's in our solar system or much further afield in the cosmos.
Yeah, well, that's pretty awesome. I mean, I'm sitting here kind of pretending like I'm sort of trying to be as normal as I can, but I don't think the audience may realize how much I'm in sort of geek wonderland over here. So now we're not talking about two fields that I sort of love to just kind of experiment in, which is all the things about the cosmos and universe and that side of it, and physics, and then also this other side, which I'm kind of a geek for evolutionary biology and all that too. So pretty cool for me, I'm telling you.
It's a fun field because you get to dabble in all of these different scientific domains. To understand where life might be in the universe, you need to understand things about the universe and to understand the history of, the formation, evolution of planets and all of that, and even how stars function, and as well as, biochemistry and organic chemistry and all these other things. So it's a good place to be.
Yeah, well, it's cool to have these kind of multidisciplinary things too, right? Because that's one thing when I felt like this was happening a lot back in the day when I was in school, is there was a lot of silos and there wasn't much crosstalk.
Yeah, and that's still unfortunately often the case. But yeah, a field like astrobiology really makes a concerted effort to break down those silo walls, because it's not just a need to combine different scientific areas. It's that there are certain ways people think in other disciplines that may inspire us in some new way that we weren't anticipating. And that's really fun. And I think all of science can benefit from that kind of thing. A mathematician thinks fundamentally differently than a chemist, and a chemist thinks fundamentally differently than an astrophysicist. And, when you have those conversations, it's where the magic happens.
Mm-hmm. That's awesome. So I wanted to start talking a little bit about Enrico Fermi and the Fermi Paradox. And, there's kind of I've seen various versions of sort of the origin story of that. They were at Los Alamos, I think, and it was a cafeteria, and he just sort of randomly makes this statement, and everyone laughs. And then, but then they kind of take a second, think about it, and say, oh, maybe this isn't a bit bigger question, then we shouldn't just be laughing this off. So can you just tell us a little bit about what this paradox is and the origin story?
Yeah, so I think, my understanding is that's a fairly accurate depiction of the origin story. And so Enrico Fermi was this extraordinary scientist of the 20th century. He was the person to build the first fission reactor, which he did at the University of Chicago in the 1930s. And he made so many fundamental contributions to physics. There's even a type of particle named after him. The fermion is named after Enrico Fermi. So when he had ideas and said things, people paid attention. And so, yeah, there's this story about them sitting around, and it was 1950 or thereabouts. And so it's the beginnings of the dawn of the space age. So they were talking about this and anticipating, what's going to happen. We're going to spread out into the cosmos, and what does that mean? And yeah, then Fermi suddenly looks up from his sandwich or whatever and makes this statement, where is everybody? And then they talk about that. And what he meant was, given that our species has got to the point where it's about to spread out into the universe, and we live in this galaxy that contains hundreds of billions of stars and probably planets, and if life isn't very, very unusual in the universe, then there are probably other places where there are species sitting around having their sandwiches and having these conversations on the cusp of their own space age. But the universe and the galaxy is also very old. And so in his head, he'd kind of done this back of the envelope calculation. He'd said, well, we have some idea of how long it might take to get from one star to another star. And we know how old the universe is, how old the galaxy is. Unless life is unbelievably rare, why isn't it here already? Why haven't we been visited? Why aren't we in the midst of this galactic empire with, spaceships flying around? That seems strange. And so that was really the origin of this so-called paradox. I don't know if it's really a paradox, but that name kind of stuck, that, based on these simple assumptions and projections, you would expect there to be stuff everywhere, but we don't have evidence of that. And then over time, that idea has been conflated with our search for signals from other life. So Fermi was thinking about stuff visiting the solar system. But there's also the question of listening for signs of technological life. And that's this effort called the search for extraterrestrial intelligence that has been going on also since roughly the 1950s and 1960s. And we have yet to obtain a signal that convinces us it's from some other species out there, whether it's a deliberate signal or whether it's just, random noise. Someone left the radio on somewhere and it's transmitting across the cosmos. And so there is a puzzle. Perhaps it's better stated as Fermi's puzzle, that unless we're incredibly unusual, there is a bit of a puzzle as to why we haven't seen evidence of other species, aliens, whatever you want to call them, out there that are equivalent to us in some way. So that's really the nature of the Fermi paradox, and it's still something we discuss and try to understand. And we can talk more about what I think some of the possible solutions might be, but that's it in a nutshell.
Yeah, that's awesome. Thank you. Yeah, and I've seen, a couple dozen different proposed or hypotheses about this and potential solutions. And as an astrobiologist, there's this idea of kind of how difficult it is or how rare it might be or what's involved in life evolving, especially to a state of sort of technologically advanced, some kind of technologically advanced state. And I know that we talk about things like the habitable zone, There's other things that people talk about what it takes. And so tell us a little bit about that and how rare is it?
Well, this is sort of still the $64 trillion question. And it's a really interesting problem. And it does relate to Fermi's paradox in some ways. So it's part of, or at least it's part of that puzzle, which is how often does life happen? How quickly does life come to exist? Where does life come from? And, the simple answer is we've been chipping away at this problem for the last 40, 50 years, and we've made considerable progress in certain areas. So you mentioned the idea of habitability and habitable zones. So that's an area that is near and dear to astrobiology. So the idea of habitability or habitable zones is really trying to answer a simple question, which is, what is it that makes a particular environment suitable for sustaining life as we know it? Now, I think parochially, we all sort of think, well, yeah, I mean, it's got to be warm enough. We've got to have something to drink. We've got to have something to eat. We don't want to be living on a volcano and so on. But scientifically, it's a complex question to answer, especially when we start to look more deeply at the nature of life on Earth. So superficially, we might say, well, it's conditions that you and I inhabit, certain kind of temperature range, enough oxygen in the atmosphere, enough food, things aren't too chaotic around us. But over the last many decades, we've learned more and more about the nature of life on Earth that has told us that actually the conditions we like are not necessarily the conditions that other life, even here on Earth, likes particularly. And so this is really to do with the discovery of so-called extremophile organisms. They're mostly microbial in nature, single-celled organisms, but it turns out they live in the most extreme conditions compared to us. Now, for them, we live in extreme conditions. So these are single-celled organisms, either bacteria or the other branch of single-celled organisms called archaea, that live at the bottom of the world's oceans, or they do live in the sides of volcanoes, or they live in places like Yellowstone, in these pools, these acid pools that, would melt your skin off if you stick your hand in as a tourist. And they are very tough. They also have all these really fascinating strategies for survival. They use different metabolic processes. There are organisms that actually respire manganese. They don't breathe oxygen, they breathe manganese in order to extract chemical energy from their environments. And so we've learned a great deal more about that sort of habitability, but we're also learning about looking out into the cosmos and trying to evaluate other places out there beyond our solar system that might be habitable. So this is a field that really didn't exist 20, 30 years ago, and it's called the field of exoplanetary science. So we have now determined that there are planets around most other stars, and some of those planets might resemble the Earth in some way. And so one of the tools we use to try to sort of sift through those possibilities are tools of evaluating the habitability of an entire planet. And for that, it's more about the habitability that we like. So does a planet have liquid water on its surface? Does it have stable seasons and so on? And as we gain a little bit more information about these other worlds, we can do things like run climate models, not about the Earth, but about these alien planets to understand whether they land in the habitable zone. Are they too close to their star to be habitable? Are they too far away? Are they in this sort of Goldilocks zone of distance from their parent star that might make them habitable? So it's a rich field. You can tell I can go on about this for a while, but yeah, so it's kind of fascinating. It's driven by the conditions we like, but it's also driven by conditions that very extreme organisms might find perfectly reasonable to live in.
Mm-hmm. In terms of the Fermi puzzle, I've seen this idea that there's the idea of life, but then there's also sort of technologically advanced life. It's like there's some life you could say that's intelligent and things here, mammals in the ocean, other species are smart, but they don't have they're not as likely to make telescopes and start probing and making radios and things like that. And that adds a layer of being more rare, right? And then there's this idea that Jupiter plays into this. So it's not only just rare Earth, but it's kind of rare solar system that a planet like Jupiter ends up being kind of rare, I guess they're saying, or some people are saying. I've seen that said. And then so all that plays into it. And I think, and that's been called this kind of rare Earth or rare solar system idea. And I know you have some thoughts about that.
Yeah, I do have some thoughts on that. Yeah, so, this idea, the rare Earth hypothesis, it's often called, is this idea that a number of people put together several years back where they kind of took a look at the contingencies in the history of the Earth that you could argue were necessary for a species like us to emerge, or even necessary for just complex life to emerge, anything more than single-celled organisms. And so there are different things you could look at, the nature of our sun, and it's sort of how active it is, the nature of things like the architecture of our solar system. You mentioned Jupiter. So Jupiter is the most massive planet in the solar system. It's 317 times the mass of the Earth, and it sits out there in the outer solar system, and it acts like a bit of a gravitational gatekeeper, and it actually modifies the trajectory of things like comets and asteroids that might otherwise pelt the inner planets much more frequently and could therefore make it very difficult for complex organisms, much less species with civilizations, to emerge on a world like the Earth. So the rare Earth hypothesis takes a number of these observations about our circumstances and tries to make the argument that, each of those factors is quite unusual. And when you combine them, it becomes really improbable that there are that many places like this out there in the cosmos. Now, as I know we've talked about a little bit before this conversation, I actually don't fully buy into that. And I think it's still a really interesting question and issue. I don't buy into it so much because of what I think is a fundamental flaw in the logic. And it's to do with the nature of probability and how we evaluate things after they've happened. It's what's called a post facto analysis. So, we're asking questions about, looking back through the history of our species, the history of life on Earth, and all of these other factors that we think in retrospect were important for us to have been able to emerge and do the things that we do. The problem with that sort of reasoning is that you end up almost assuming at the outset that there's only one pathway to a species like us, right? And you go back and after the fact, you interpret things, right? And interpreting things after the fact is really tricky. What you ideally would do as a scientific experiment is somehow run 1 trillion experiments starting with the origin of the Earth 4 billion years ago, and you run those forward in time, and you see how many of those experiments, each slightly different, wind up producing something like us. Now, of course, we can't do that, or at least not easily and not at the moment. But, if we could, we might learn that actually there are multiple pathways to a species like us. We might discover, like the rare earth hypothesis, that actually there's really only one possibility, and therefore we are pretty unusual. I have my doubts about that. I think it's more likely that there are many ways to end up with something like us. And I think it also speaks to the way we frame this argument about other technological life out there. We may be very unique, and that I would definitely say is a possibility, that in the entire observable universe, there may only be one place that is exactly like this, with creatures exactly like us, with, YouTube and Zoom and smartphones and so on. But there could be trillions of other species that are similar, right? That have other versions of all these things, or, are equally sophisticated. It's just that, you can be unique, but not improbable. is what I think is a likely solution to this. And, this idea of post facto analysis, we encounter it all the time in our everyday life, right? We suddenly, we bump into someone on the street and, we haven't seen them for 10 years. It's like, oh, wow, that's crazy. Last I saw you, you were in Kathmandu, up a mountain. What are you doing here? And you then tend to talk with that person about, well, if this hadn't happened and if that hadn't happened, none of this would have taken place. But of course, there might have been 1,000 different ways that you actually end up meeting on the street. You just don't know about those, right? Because you can only track back the one that actually happened in the end.
Interesting. Yeah, and another one of the other sort of solutions or ideas about why we don't see anything when we look out there is this idea of a great filter, which is a little scary, but this idea that any technologically advanced society has to get through this filter. Like, I think the idea is maybe they get to a certain advanced state, and maybe they do something like have nuclear annihilation or something like that, and they don't get past that point. And and I think I've seen that people are saying, well, we don't know if we're on which side of that filter we are right now. But what can you say about that proposal?
Yeah, well, I think it feels like it has a ring of truth to it. I think probably we all at the moment, if you're a thinking human being, you can't but help look around at the world and say, are we on the cusp of doing something really bad to ourselves? Have we already done it? And it's just a matter of time. So I think the basic idea is a good one, that, there may be certain situations that species like us, technological species, that learn to manipulate their environment in a way that is much more extreme than other organisms. I mean, other life on Earth has manipulated the environment. Plants manipulate the environment by pumping out oxygen and so on. And actually, back when that really started happening 2-3 billion years ago, it was really detrimental to all sorts of things in the Earth's environment. It's just over time that everything settled and new organisms emerged in this oxygen-rich atmosphere. But we do it at a rate that exceeds, as far as we know, anything else that has happened in the history of life on the Earth. And that may be typical of species that learn how to manipulate their world, build technology, in the way that we have. And so I think on the face of it, the idea of a great filter is certainly not a bad idea. And it is very interesting. People have also talked about, the implications of a great filter for the kind of work that someone like me does, searching for signs of other life. So for instance, the great filter explains the absence or apparent absence of other technological life in the universe, whether in signals or coming through our solar system, because it says, well, as soon as you get to the point where you would be capable of either traveling from star to star or transmitting signals, you basically kill yourself off. You become extinct. But that is also predicated on how often life happens anywhere, any sort of life. And so there's some rather gloomy ideas about, if we go to Mars and we do find evidence of simple life having existed or still existing on Mars, that's actually really bad news, because what it tells us is that life really does happen very often. So if we found life on Mars, and this is part of the motivation for astrobiology, one other example would actually tell us that statistically life is happening all over the place in the cosmos. So if we find that life out there on Mars, it tells us life is happening all over the galaxy, all over the universe, but we still haven't seen it as technological life, which means there probably is a great filter. So it's, I mean, I don't know if I completely buy that, but that is, that's part of the idea. And, it's something I think we perhaps should take seriously. And we don't know, as you said, which side of the great filter we're on. If we're through the great filter and we survived, woohoo, then we need another way to solve the Fermi Paradox. But if we're on the wrong side, if we're approaching the great filter, then, well, our fate is sealed. Yeah,
it's something that I think that we should maybe be humbled about. There's another solution or part of the solution is this idea of sort of dangerous world, I guess, right? I don't know if that's quite the right technical term, but I think I've seen that thrown around, of this idea that, it's a dangerous world. So when you're smart enough to have the technology to transmit and you stop doing it, or you try to hide it because you go, there's a dangerous world out there. I don't want anyone to know where I am. What are some of your thoughts about that?
I mean, it's an option, right? we don't know what the answer to this is. I mean, I can talk a little bit about my personal feeling on that in a moment, but the dangerous world is definitely an option, right? And in fact, I've written about this in the past, thinking about even information can be dangerous. And so a species might decide that, I don't want to pick up a transmission from some other alien species, because suppose they transmit some information that allows me, I don't know, to build some terrible weapon. And that is the great filter. I eliminate myself. They don't need to come and invade. They can just send the right information, and that can be like a virus. It can be absolutely devastating to have new information about certain things. And so the safest thing is to both not transmit and not listen, to basically isolate yourself from the cosmos for fear of what might happen if you made contact. That is certainly one of the ideas out there. I mean, at the risk of being a bit of a party pooper, my feeling about the Fermi Paradox in both its forms, whether stuff comes visiting the solar system or whether you pick up signals, is that there is an assumption in both of those pieces of the paradox that we actually are really good at noticing what's happening in the universe around us. And I don't think we are, at least not as good as we perhaps could be. So, if there are species traveling through the universe, visiting different planetary systems, that would have to coincide with our existence at the moment. So it's a pretty narrow window of time. Even a few hundred years ago, would we have noticed if some alien mothership passed through the solar system, took some pictures and went somewhere else? I don't think so. We probably wouldn't have noticed because we weren't looking in any sort of consistent, coherent fashion. And the same is true to some extent with signals. We actually know that even though we've been listening for radio signals coming from the rest of the galaxy, listening for structured information-carrying signals, we've really not had any evidence that we've found any so far. But if you look at the range of frequencies that we've listened to, how long we've listened, in which bit of the sky we've pointed our radio telescopes, it turns out to be a tiny fraction of the total range of possibilities. And people who work in SETI acknowledge this. And it's part of why they hope to keep doing this, is that they know we've only scraped the surface. So part of the answer could just be that we're kind of blind and deaf still, even though we think we're so good, and in many ways, right, we're remarkably better than we were a few hundred years ago at studying the universe with our telescopes, with our radio receivers and so on. It's still a small fraction of what you might really need to convince yourself that nobody else is out there. That's my feeling about it. But these other ideas may be valid too. There's also the dark forest idea, which is an even more sinister version of the idea that you mentioned. The dark forest is that species that are capable of interstellar travel and capable of seeing or sensing the presence of other technological species basically eliminate them as soon as they've detected them, because the possibility of being invaded or being eliminated themselves is too great. And so you just eliminate them. That's the way to keep yourself safe in a dangerous universe.
Yeah, and I've seen some kind of mixing of some of these together, like the civilizations that get through the great filter then kind of fall into the dark forest mode and things like that.
Yeah. No, I mean, it's great fodder for, I mean, some of it, it's useful stuff to think about, because maybe one of those solutions is actually what's going on. And But we do know that we could do a better job at looking and listening, and that might help resolve this problem.
Yeah, we can't do anything about is the time part though, right? We're still only within the small time window. I mean, like people talk about 50 years or 100 years, like you said, and that's just such a tiny speck.
Absolutely. And, ironically, if there is a great filter, it might prevent any species from reaching that magical moment where they learn that they're not alone in the cosmos. And maybe if they did learn that they were not alone in the cosmos, it would change things and they wouldn't face a great filter. There'd be some solution that they would learn from other species.
Yeah, that's where I kind of wanted to go next a little bit. I mentioned that I heard about this overview effect where some astronauts come back with like a sort of transformed, kind of in a really significant, profound way, where they sort of realize how fragile Earth is. They sort of see it as this little speck in this dark, hostile universe and little itty bitty thin, fragile atmosphere, and the whole thing is fragile. And they come back, with that kind of new perspective. I mean, and that seems to be kind of a follow on from what you were just talking about. Maybe talk a little bit about this idea, like if we can see ourselves in this kind of precarious position in the universe, maybe we could then stop arguing about which theory is right, and maybe start thinking about what we do next.
Yeah. So I mean, the overview effect is very interesting. I think there's kind of two pieces to it that astronauts have talked about. One is, yes, seeing the actual fragility and the sort of singular nature of the Earth, certainly within our own solar system. You get out into the blackness of space and you look back and there's this island, and it's bright and it's beautiful, but it's an island, and it's, as you say, it's got this very thin layer of atmosphere compared to the size of the planet. It's this incredibly fragile looking thing. But they also, as part of the overview effect, gain this sense of unity. This idea of they see that there are no boundaries between countries, that there is connection across continents, across oceans. It's all one system, right? It's this extraordinary system. It's the planetary system, the geology and geophysics, but then there's this biosphere that's infested this world. I mean, infested is not a very poetic way of putting it, but it's one way of thinking about it. This, life is this extraordinary, exquisite phenomena that has been tenacious, and has produced so much magical stuff. I mean, evolution is just this incredible source of originality and innovation, constantly inventing and reinventing the nature of organisms and so on. So I think it's this combination of the beauty and unity of the Earth, of life on Earth, and, it's one step from the surface of the planet to a very hostile universe. And so, yeah, I think if we could all somehow gain more of that perspective, right, one would hope that it might direct our attentions and our behaviors in a more productive way. And the great filter, and even the current absence of signs of life elsewhere in the universe, you could take that and say, well, maybe we are alone, right? In which case, wow, we better be careful. There's not only is there no plan B, there's nobody to notice if we're not here anymore except us, right? And so, what do we want our human future to be? What do we want the future of life on this planet to be? Do we have responsibility, but also just for our own sense of moral rightness? Is it okay for a species to knowingly damage other species and to damage the world that produced it? I'm not sure, right? If there haven't been other species capable of our level of cognition, we are the first to face that conundrum. And I think that comes with a great deal of responsibility, as much to ourselves as to anything else.
We usually think of our daily outrages as the big problems, but zooming out, they start to look like static. Noise. If we're the only ones here to notice the beauty of this world, then how we treat each other, the only other cognitive beings we know of, isn't just a political choice, it's a cosmic one. The next time you feel that surge of outrage, try to remember the silence of the hundreds of billions of stars. It might just give you the perspective you need to choose a different path. That is it for this episode of the Outrage Overload podcast. For links to everything we talked about on this episode, go to outrageoverload.net. Outrage Overload is a Connors Institute podcast. The Connors Institute for Nonpartisan Research and Civic Engagement at Shippensburg University works to disseminate high-quality, nonpartisan information to the American public around issues of societal well-being, democracy promotion, and news literacy. If you found this episode valuable, please share it or leave a review. It really helps. Thanks for listening, and I'll catch you next time.